Hello students, welcome to Lecture 5, Atoms and Identifying Elements. Before we start, please turn to pages 6 through 8. Let's first summarize the structure of the atom. The atom structure is summarized as the atom having a small, dense, positively charged nucleus surrounded by mostly empty space of negatively charged electrons. Now let's discuss the components of the atom. First, you have the nucleus, or the small, dense, positively charged center of the atom, with particles called neutrons and protons inside of it, collectively known as nucleons. Neutrons and protons are collectively called nucleons because they're both particles found inside the nucleus. Now, outside the nucleus, you have a large, mostly empty surrounding space that contains electrons. So if you look at this, you have a dense positively charged nucleus with nucleons found inside them, where you see the protons are shown by purple positive spheres and the neutrons are shown in the nucleus by the blue neutral spheres. Outside of it, you have a surrounding space of negatively charged electrons where the electrons are represented by green-gray spheres that are negatively charged outside the nucleus. So next, let's discuss subatomic particles, or particles that you find inside the atom. The three subatomic particles, or particles inside the atom, are protons, neutrons, and electrons. And the masses of each of these three subatomic particles and the mass of an atom, known as the atomic mass, are both measured in AMU or U, which is short for atomic mass units. All right, now, let's go over each of the subatomic particles, but before we start that, just note that relative mass is the mass used to compare the masses of each of the subatomic particles to one another. It's not the actual mass, it's just the mass used to compare their masses against one another in terms of how big they are. The actual mass is given in grams, while the relative mass is given in U or AMU. All right, so let's start with the proton. A proton, as shown by these purple positive spheres in the center of the atom, is located in the nucleus. All right, and each proton carries a relative mass of 1 AMU or 1 U. All right, the actual mass of each proton in grams is 1.67 times 10 to the negative 24th grams, and the charge of each proton is positive 1. The way you can remember the charge of each proton is the P in proton stands for positive, so translating that, that tells you that each proton carries a charge of positive 1. Next, we have neutrons, and neutrons is shown by the blue neutral spheres in the center of the atom. That proves that neutrons are located inside the nucleus, just like the protons are. Each neutron has a relative mass of 1 AMU or 1 U, and the actual mass of each neutron in grams is 1.67 times 10 to the negative 24th grams. And the charge of each neutron is 0. The way you can remember this is neutron sounds like neutral. And mathematically, what number do you think would best represent neutral? I would say 0, so that's how you remember that the charge of each neutron is 0. All right, finally, the electrons, as shown by the green-gray negative spheres outside the center of the atom, as you can see, obviously are located outside the nucleus. Each electron has a relative mass of 0 AMU or 0 U. The actual mass of each electron in grams is 9.11 times 10 to the negative 28 grams, and the charge of each electron is negative 1. One more thing you should note here is that the relative and actual mass of a proton and a neutron are the same, while the relative mass and the actual mass of an electron are much less than that of what a proton or a neutron would be. Okay, so there you go. Next, let's discuss electrical neutrality. Electrical neutrality means atoms carry a charge of 0 or no charge overall. Now, atoms are electrically neutral, or carry a net charge of 0 overall, because, very simply put, the number of protons equals the number of electrons. This is the official explanation, that's it. But the way you can think about this explanation is if the number of protons equals the number of electrons, the number of positive charges from the protons equals the number of negative charges from the electrons. So those two charges basically balance or cancel each other out to yield a charge of 0 or neutral for the atom overall. All right, so let's try an example so we can get a better feel for this. The example asks us to explain why an atom of boron is electrically neutral. Based on what we know, a boron atom is electrically neutral because it has the same number of protons and electrons. That's our official explanation. Right, so let's get down into specifically how many protons and electrons it has that are the same. So down here we have a diagram of a boron atom. If we count the number of protons in the nucleus as shown by the purple positive spheres, we have a total of 5 protons. All right, if we count the number of electrons outside the nucleus, as shown by negative gray-green spheres, we have a total of 5 electrons. So to make the answer to this example more specific, we have specifically 5 protons and 5 electrons in a boron atom. Next, we have the atomic number symbolized by capital Z. The atomic number represents the number of protons inside an atom's nucleus, which is used to identify the element. Okay, this is because the element's identity always depends on the atomic number and number of protons, so make sure you remember that. For example, nitrogen, as you've seen down here, has an atomic number of 7, as you'll see soon, and based on what we just learned up here, it therefore also has 7 protons. No other element has an atomic number of 7 or 7 protons, only nitrogen does. Based on this idea, the atomic number and the number of protons are always the same for atoms of the same element. That is, as long as you have an atom of nitrogen, for example, you'll always have the same atomic number of 7 and the same number of protons, which is also 7 based on the atomic number. All right. Now, the atomic number's location is near the bottom left corner of the elements box on the periodic table, and it's listed as a bold number. Okay? So if you pull up the periodic table as shown in the key, the bottom left bold number for carbon, or C, is called the atomic number. So for C or carbon, as we see here, the atomic number is 6. So it, therefore, based on the definition we just learned, also has 6 protons. Based on what we just saw, we also know that all atoms of carbon have an atomic number of 6 and therefore 6 protons no matter what. If we try for sulfur, we see that sulfur's bottom left bold number is 16, right? So for sulfur, its atomic number therefore is 16, telling us that it has 16 protons. The atomic number 16 and 16 protons are the same for all atoms of sulfur. All right, now let's try 2 examples using what we learned. First, which 2 quantities are used to identify nitrogen atoms, and state the specific numbers. All nitrogen atoms have the same atomic number and the number of protons, as we just learned up here. All right, since nitrogen, or N's bottom left bold number is 7, we know that all atoms of nitrogen specifically have an atomic number of 7 and 7 protons. Next, we have to find the number of protons and the atomic number of an atom of oxygen 18. Don't worry about this number 18, we'll cover that in a second. But we know that no matter which version of oxygen we have, whether it's oxygen 16 or oxygen 18, as long as it's oxygen, its atomic number and the number of protons are always the same, both shown by the bottom left bold number of 8 in oxygen's element box if you check it on your own, or O's element box. Hence, our answer is oxygen 18 has 8 protons and an atomic number of 8. Okay? Next, let's discuss the nuclear charge, or the charge of the nucleus. The nuclear charge equals the number of protons in the nucleus with the plus sign following it at the end. This is because only protons contribute a charge to the nucleus, plus 1 charge each, while neutrons carry a neutral charge or charge of 0. So they contribute basically nothing to the nuclear charge. Since only protons in the nucleus contribute a charge, the nucleus always carries a charge with a positive sign. All right, let's see how this works with an example. The question here asks us to find the nuclear charge of a boron 11 atom. We know the nuclear charge of boron 11 equals the number of protons in boron 11's nucleus, based on what we just learned, right? We also know from before that boron's number of protons equals its atomic number. Putting that together, we know that boron's atomic number will give us the number of protons and the number to put in front of the plus sign for boron 11's nuclear charge. Boron's atomic number is 5, so that tells you that you have 5 protons. That also tells you that you have a nuclear charge of 5 plus. So there's your answer. Boron atom's nuclear charge is 5 plus. Let's quickly explore why. If we look down here, we see that we have 5 protons in the nucleus of boron 11 shown by 5 purple positive spheres, and 6 neutrons in the nucleus shown by 6 neutral blue spheres. To find the total charge of boron's protons in the nucleus, use it to multiply the number of protons, which is 5, by the charge of each proton, which is plus 1. So you have 5 times plus 1, or plus 5 as the total charge of protons in the nucleus. Now, the total charge of borons and neutrons in the nucleus is found by multiplying the number of neutrons in the nucleus, which is 6, by the charge of each neutron, 0. So you have 6 times 0, or 0 as the total charge of neutrons in the nucleus. Putting that together and adding them together, the total charge of boron 11's nucleus is 5 plus, which shows that 5 protons are the only particles that contribute a charge, while the neutrons don't affect or contribute to nuclear charge at all. Okay? Now let's discuss mass number. Mass number, symbolized by capital A, represents the sum of the protons and neutrons in the nucleus, given as a whole number. So the mass number really gives us a sense of what the mass of the atom could be. And the reason, it makes sense if you think about it, that the sum of the protons and neutrons gives you the mass number, or a sense of the mass of the nucleus. Because if you look back, you'll see that neutrons and protons, in terms of relative mass, are the only 2 particles that have a relative mass at all. So those are the only 2 particles that should be considered in the mass number. All right, so the equation for mass number is equal to the number of protons plus the number of neutrons. And the formats of mass number are 4 different types. You could get a superscript to the left of the element symbol, like this at the top, that represents the mass number. So here would be 14, here would also be 14. You can also get a number following an element symbol or a number following an element name, and that number following the element symbol or element name also gives you the mass number. So in carbon-14, 14 is the mass number. In C-14, the 14 that follows after carbon is the mass number. All right? Now, I also want you to note that the mass number and the number of neutrons can change for atoms of the same element, but as we know from before, the atomic number and the number of protons must be the same for all atoms of the same element. This should make sense to you because the only two things that are used to identify an atom of any element are atomic number and number of protons. So those are the only two things you really cannot change if you want the same atom. But I never said anything about mass number and number of neutrons. So you can change the mass number and the number of neutrons because they do not determine the identity of the element. So if you change them, nothing really happens. So the mass number and number of neutrons can change, and you can still have an atom of the same element, but the atomic number and the number of protons must always be the same for all atoms of the same element. Okay? So now let's try an example of calculating mass number. This question says a carbon atom has 6 protons, 6 electrons, 7 neutrons. Find its mass number. Right? If we do this, all we have to do to plug into the mass number formula is we just have to add the number of protons plus the number of neutrons to get the mass number. If we plug in, we get 6 protons plus 7 neutrons gives us the mass number of 13 for this atom of carbon. If we look down here for this atom of boron, we'll see that we have 5 protons shown by the 5 purple positive spheres, and the number of neutrons shown by the neutral blue spheres is 6. So if you do 5 protons plus 6 neutrons, you see that the mass number of this boron atom is 11. Okay? Next, let's discuss finding the number of neutrons and electrons in an atom only. As we know, in atoms only, the number of electrons always equals the number of protons, since an atom is neutral overall. Based on what we already know also about atomic number, we can also say that the number of electrons equals the number of protons and the atomic number for an atom. All right, next to find the number of neutrons, all we have to do is just rearrange the formula for mass number from before, and that gives you that the number of neutrons equals the mass number minus the atomic number. All right, so let's try 2 examples of this so we understand this better. So first, find the number of electrons and neutrons in a phosphorus-32 atom. We know that for atoms only, that the number of electrons equals the number of protons and the atomic number. Phosphorus, or P's atomic number, if you check, is 15. So the number of protons and electrons is also 15 here, since we have an atom. So therefore, you have 15 electrons in a phosphorus-32 atom. All right. Next, the number of neutrons equals the mass number minus the atomic number. Right? We know from before that a number following a chemical symbol or name is the mass number. So the 32 following phosphorus and phosphorus-32 is phosphorus-32's mass number. So the mass number here is 32. And then we also know that the atomic number of phosphorus, or P, from the bottom left bold number from P's element box is 15. So plugging in number of neutrons equals mass number 32 minus atomic number 15, giving us 17 neutrons in an atom of phosphorus-32. All right, next we need to find the number of electrons in a titanium atom. We know for atoms only that the number of electrons equals the number of protons as well as the atomic number, right? So just look up the atomic number of titanium, or Ti, in the periodic table to find the number of electrons. If you do that, which you can do on your own, and if you check the periodic table, you'll see that the atomic number of titanium, or Ti, is 22. So that also tells you they have 22 protons, and it also tells you, since this is an atom, that you also have 22 electrons. So there are 22 electrons in an atom of titanium, okay? Next, let's quickly discuss the periodic table. The periodic table is a table that arranges elements in a systematic order, meaning the order is done based on a fixed planar system. And the periodic law, which was discovered hundreds of years ago, states that the periodic table is arranged in order of increasing atomic number. Put another way, if you incorporate the idea that atomic number equals number of protons, the periodic law also states that the periodic table is arranged in order of increasing number of protons. So that's another way you can think about it, all right? Now, the periodic table is arranged in groups vertically up and down, and in periods horizontally left to right. Specifically, groups are vertical columns going up and down like this that are labeled 1 through 18 on the periodic table, labeled by number. It's sometimes labeled with the name, but not always. Right, but it's 1 through 18 here, on the top here. Now, periods are horizontal rows labeled 1 through 7 on the periodic table, and they're each labeled by number. All right, so you can see the periods labeled to the left of each period here like this, if you look on your periodic table. It's also worth noting, by the way, that elements in specific periods and groups will tend to have similarities, as you'll see later. Finally, let's discuss the 3 types of elements you'll encounter in chemistry: metals, nonmetals, and metalloids. All right, but metalloids are the first type I want you to memorize because from there you can really determine the other types of elements really easily. Metalloids are the 7 elements on the bold steps of the periodic table here, which I want you to memorize, and they are B, S, I, G, E, A, S, S, B, T, E, and A, T. The best way to memorize these 7 metalloids is be silent, Gerald, as Sabrina tells a tale. And that stands for the 7 metalloid elements, which are boron, silicon, germanium, arsenic, antimony, tellurium, and astatine. All right, now, any element to the left of the metalloids on the steps is a metal. So, for example, Na and Fe are metals since they're left of the metalloids on the steps. Any element to the right of the metalloids in the steps is a nonmetal. So, for example, F and S are nonmetals since they're right of the metalloids on the steps. One exception I do want you to know is that even though H is to the left of the metalloids and the steps, H is actually a nonmetal. So note that exception, that H is a nonmetal even though it's to the left of the metalloids on the steps. That hydrogen is a nonmetal even though it's to the left of the metalloids on the steps, all right? So there's your one exception, but that's really it. You can read over this on your own, but we'll be revisiting that at a future date, and please make sure you complete these practice questions for the next class. And for these practice questions, just look back at the examples because they'll really help you from this lesson. Thanks, see you tomorrow, bye.